Okay, thanks, Chair. So my name is Zhang from Tsinghua University. The first author of this paper, Xiaoqin Xie, who graduated from Tsinghua. So we know each other for about more than 20 years. So she asked me to help her to do the presentation. And I read the paper for several times and find some feelings. Right? Okay. The topic is the efficient community search based on the relaxed k-truss index. So this topic is similar to the previous talk, right? Also the community search, but the previous paper, they focus on the k-call model. This paper focuses on the k-truss model. There's many real-world graphs and social network, protein, and traffic networks. So this networks often they're represented as big graphs. Right? So to search in a big graph is not easy. So because of the efficiency and effectiveness, so normally the people they use community to discover informations. So the community is a subgraph closely connected internally. For the community search, it's hard to find a densely connected community. And so just like this figure at the bottom, you can see that for the query node, you can give several nodes, the 1 and the 2, and looking for it in a big graph. Like the graph in the middle, you can find this that the node 1 and 2 that included in the subgraph inside the circle. So the output of it is a community. So that's community search. There are several community models in the previous talk. They use the k-call model, and here we use k-truss model. So the k-truss model means that each edge is contained in at least k-2 triangles. So by using the stable triangles, the k-truss can guarantee the structural cohesion. So the left of this picture is k-call. On the right side is k-truss. You can find the 3 truss, 4 truss, and 5 truss in different colors. So next, I'm going to introduce our motivations, the why we want to do this work. So the k-truss is a good model to the community search. So, but this model still suffer from several issues. So the first thing is, it's too strict. So if you cannot find enough triangles in the subgraph, then it will not be a k-truss community. Look at the graph, the picture in the model. Right? This is protein networks. So the subgraph in the middle in the square. As a human, you will recognize, right? It is a community. But if we just apply k-truss model to this graph, so it won't fit into the framework. So we want to solve this problem. The second problem with it is, so many k-truss community search algorithms, they spend polynomial time or more, so it's difficult for them to handle users' real-time search requirements on large networks. We want to decrease the time here. There are 2 challenges. So first one is, if we want to solve these 2 issues, we need to solve 2 challenges. The first one is how to simultaneously to describe the personalized relaxed cohesion and the structural cohesion. The structural cohesion here means the cohesion provided by the k-truss. The personalized relaxed cohesion means something like this, right? It is a community, but does not follow the k-truss definition. The second challenge is how to flexibly combine these two cohesions together in a unified disk structure. Let's explain them one by one. For the first one, how to describe simultaneously describe relaxed personalized cohesion with structural cohesion requirements. So the relaxed cohesion can be measured by some special features such as modularity that are used very common in the community detection. The structural cohesion can be exploited by the k-truss-like models for community search and how to merge them. Here we propose a relaxed community search problem. So we define a new problem, try to combine them together. So to make restrictions on either the strict structural cohesion or relaxed cohesion, expressed by a concept which is called community strength. We will define it later. The second challenge is for how to put them together in a unified disk structure. Right? So we define a relaxed k-truss index tree that combines these two together. We use relaxed levels to store the communities with relaxed cohesion. We use truss levels to store the nested communities in strict k-truss structures. For these two challenges, we are going to do some definitions. First is to define the community strength. This is a core concept in our model. So this community strength can have different formats. So we can use the modularity to measure the community strength. So modularity is used in the community detections, such as this formula in the middle. We can also use the label propagation probability to measure the community strengths. Here is the formula at the bottom. Based on the community strengths, then we can define a new problem, which is called the relaxed k-truss community search problem. So given network and the query node set, so a parameter k, the relaxed k-truss community search problem is to find the community with the connection properties and one of the following cohesion properties. There are three properties. The first one is connectivity. So it is a connected subgraph contains all the query nodes in Q. Right. The second is structural cohesion, and the third is relaxed cohesion that follow their original definitions. So the essence of the relaxed state idea lives in that structural cohesion and relaxed cohesion conditions do not need to be met simultaneously. So because they do not need to be met simultaneously, then we can put them together like the picture to the right. So this picture defines the relaxed k-truss index model. We call it RT index. Give a graph. It contains an index tree plus with a map. This top, that index tree. At the bottom is a map. So the index tree has two levels. The top level is relaxed levels. The root of it is original graph. For this graph, we can use community detection method to extract communities. Here, for this graph, we extract three communities. So these two, both of them, they compose the relaxed levels. Below that, so for each of the community, there are the subgraphs. For these subgraphs, we partition them. We use the k-truss the methodology, right, to split them from big to smaller. Let's go down the tree. So at the bottom, at the leaf of the index, we have a map to map all these k-truss, these leaves, and to all these nodes at the bottom. This is the map. So we think that this design can ensure that our search methods can find not only k-truss community, but also with non-k-truss community with cohesive features. So this is the core design of our method, RT index. And for this index, we have several algorithms. So the first one is how to construct it. Right? The top is the original graph. Right? So the output, we want all this index with the map. We put in the map into different communities. Right? And in the step 3, for these communities, we just decompose them into the communities in different k-truss structures. You can see the 3-truss, 4-truss, and 5th-truss, and 6th-truss. For this index, when you search it, and how to search communities, the input, we got a query node set. We got a K, we got RT index. So first, with this query, let's start the construction. We start from the top, right? But for the search, we start from the bottom. Here's the query, 1 and 7. Search, we find it in the array in the bottom, and try to find, okay, node 1 corresponding to the leftmost node, and node 7 to the second one. So both of them, they have a common ancestor. So that's 1, 2, 3, 4, and to 8. So that is the community, right, for it. So this is we can find the k-truss. If not, we will give the basic communities in the relaxed levels. So for these two algorithms, we calculate the complexities, time complexities. The details of how to get the result, you can find it in the paper. Next, we go to the experiments. So for the experiments, we want to prove 3 things. Right? This requirement 1, how does this method perform compare with other methods? Requirement 2, how this index help us to achieve flexible, personalized, and linear time searching. And third one, how do different parameters impact community searching performance? We use 3 data sets, DBLP, Facebook, and Amazon. We use 5 measurements from PR, LU, F1, and the time. The baselines we selected, the 3 baselines, the NES IDX, WC index, and 2-level indexes. So the first one, it is inspired us, right, to design our RT index. So the first experiment, we try to answer the question in the RQ1 and RQ3, the performance evaluation of community search and various K parameters. So from the figure, so this parameter K defines the structural constraints. So you can see from these pictures, these graphs, with K increasing, our method always achieves the best performance with the highest F1 and LOU. That proves the effectiveness of our method. So for the RQ2, we do ablation study on relaxed level. So this experiment to evaluate the effectiveness of the levels on community search, we can find that RT index with relaxed level outperforms without relaxed level on precision, LOU, and F1 performance. But you can also see we did not got the better recall on it, because with the relaxed level after without performance, it got a more strict constraint that they will have a higher recalls. So also for the requirements 2, we evaluated performance on different community strengths measurement, because there are many community detection methods which correspond with all of them. They have different community models, such as modularities, such as modularity in the low-end method and the label propagation probability, edge increasing, and greedy modularities. So for these 4 cases, we can find that LPA performs best on DBLP, but low end does best on the Facebook. So this result helps us. Okay, for the relaxed levels, we need to choose different community strength measurements for the relaxed level according to different networks. There's no a single method for different data sets. For the RT index construction, we do the evaluation on the time or the scalabilities. We choose different size of the network from the original network, from 10, 25, 50, 77, and 100. You can see that the time cost increased super linearly with network size. This is consistent with our theoretical calculations, the time complexity. For the requirement 3, we do the effectiveness evaluation and various network size. So we can find that all the measurements, they have an increasing trend. It indicates that more data is conductive to obtain complete community information and can achieve more accurate community search results. Here is the case study. If we use the pure k-truss method, we won't find these communities, because for 155099, it is not included in any of the triangles. So we cannot find it using the k-truss method. But in using our method, we can find it with k equals 3. This illustrates that we have more powerful. We can find more communities in real-life scenarios. So here's conclusions. We define a relaxed k-truss community search problem, and we define an RT index, try to solve it. We think that our method try to bridge the methodology in the community detection with the community search. Okay, that's all. I will try my best to answer questions if you like.